All right, folks, this is the last segment for Chapter 5 lectures, pages 5.22 to 5.25, and it's just another look at net ionic equations in a little more detail, and that'll wrap up Chapter 5. So I'm looking at page 5.22, and there's my molecular equation. I've written each of these as if they're sort of molecules. They're not molecules because these are ionic compounds, but I've written them in what we call molecular equations. So they're all my molecules. So there's my molecular equation: aqueous, aqueous, solid, and aqueous. If I talk about the total ionic equation, I'm going to break up aqueous soluble ionic compounds. So I'd say, well, wait, there's no iron 3 chloride in that solution. What there is iron 3 ions and 3 chloride ions. And again, if that doesn't make sense, stop the video, take a look at that. I've got the 3 sodium hydroxides. There's no sodium hydroxide in solution. There are 3 sodium ions and 3 hydroxide ions. Now again, ions, I should say aqueous, 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 but I'm being lazy and I'm saying all ions are aqueous. On the other side, I've got iron 3 hydroxide. It's a solid. If we looked at our solubility rules, we'd see it's not water soluble. So that one's treated differently. And then I've got the 3 sodium chlorides. There's my total ionic equation. And sort of taking those formulas and saying, well, that's not really what's in the water. What's really in the water is iron 3 ions, chloride ions, etc. And now if I'm going to say, well, okay, that's the sort of honest, full picture. But if I said, let's ignore anything that stays exactly the same on both sides, I go, well, that and that are identical. 3 chlorides on the reactant side, 3 chlorides on the product side, no difference. 3 sodium ions, 3 sodium ions, there's no difference. So the net ionic is Fe3 plus 3 OH minus gives me this iron 3 hydroxide. Now, here I might as well write aqueous and aqueous. So there we go. Molecular equation, it's balanced. I've got all the phases. Total ionic, I break up soluble ionic compounds. Net ionic is ignore anything that was unchanged. You can think of it as algebra. 3x, 3x. 3y, 3y. When they're the same on both sides, we can cancel them. Let's look at page 5.23. A little different, a little variation. Example number 3. Well, there's my molecular. If I want my total ionic, my ionic equation, I wouldn't write sodium hydroxide. I'd write sodium ions plus hydroxide ions. And then I've got HCl. Well, we made a flashcard that said HCl is one of the 5 or 6 strong acids. There's no HCl in that solution. It's a strong acid. What I have there is H plus CO minus. And I know that because it's a strong acid, and that's what strong acids do in water. If that doesn't make sense, stop the video, think about that, like, wait, why does he break that up? What are the strong acids again? On the other side now, I've got water. Now, water's not a soluble ionic compound. Water's not a strong acid. It's just a liquid. It just stays as a liquid. From the total ionic, total molecular, to the total ionic, there's no difference. Sodium chloride, aqueous, our solubility rules, plus the fact that it says aqueous, says, oh, that's actually sodium ions and chloride ions. So there's my total ionic equation. I'm going to do the same thing. What is identical on both sides? Well, sodium and sodium. I'm going to ignore those. Chloride and chloride, identical on both sides. So I can cancel them. You can think of it as canceling like you would with an algebraic expression. So my net ionic is OH minus plus H plus gives me liquid water. Aqueous, aqueous. Let's try one that's just a little messier in terms of having the numbers. Example number 4 here. Same thing. 3, strontium chloride. 3 strontium plus 6 chloride. Now again, if that doesn't make sense, it's a good time to stop the video and say, wait, how do you get the 3? How do you get the 2? Got these 2 lithium phosphates, gives me 6 lithium plus 2 phosphates. Now again, if that doesn't make sense, you want to stop and think, well, how did that work? How did I know the PO4 stays together? Well, in chapter 3, I made a flashcard that says that's phosphate. So again, if I don't know that, I'm sort of sunk at this point. On the other side, there's my solid. That's not going to break up. SR3, PO42, solid plus. Lithium chloride says aqueous. And our solubility rules would tell us that lithium compounds, chloride compounds are soluble. So I've got 6 Li plus 6 chlorides. Net ionic, ignore anything that's unchanged. The spectator ions. Spectator ions, spectator ions, spectator ions, spectator ions. Right? They're just sitting on the sidelines watching. So my net ionic is 3 of the strontium ions, aqueous, plus 2 of the phosphate ions, gives me strontium phosphate solid. Now, that just makes the numbers a little weird, but it's the same exact thing. I just had to use the coefficients and think about how many ions are actually breaking off there. Okay, page 5.24, there are our rules. If everything is written as if they're compounds, molecular equation. If I break up soluble ionic compounds, solubility rules, and I break up strong acids that we had to memorize, that might be a good time to stop the video and say, oh wait, can I name the 5 or 6 strong acids and then come back? Well, I'm going to write them right now. HCl, HBr, HI, HNO3, H2SO4, and ClO4, I think in our book. ClO3, one or the other. Okay. Now, let's start without an equation. If we have to predict the products, balance the equation, and then write the molecular, the total ionic, and the net ionic, we can do that. So it says reaction of HCl. I recognize that as a strong acid. Sodium carbonate, I might not recognize as a base, but I'm going to write the formula because I know how to write it from chapter 3. So I'm going to say HCl plus Na2CO3. Now I'm thinking, well, wait a minute, this is actually H plus. H plus is going to try to stick to what kind of charge? Well, it's going over here looking for something with a negative charge. The other thing we get with every acid-base reaction is we always get an ionic compound. Those would be the leftovers, chloride and sodium ions. So if I said, okay, well, let's see, let's balance this thing. This CO3, 2 minus. I'll put an arrow there. Now to make that neutralize, all the acids used up, all the bases used up, I'm actually going to have to put a 2 right there. That's going to give me, well, let's do this one first. NaCl. I know the H is going to react with the anion base. I've got this other cation and anion left over. They go together. Our rules of thumb for Chem 51 are an acid-base reaction gives me an ionic compound and water, and sometimes we get CO2. So let's look at what happens if I take that H plus, match it up with the CO3 carbonate. I'm going to get H2CO3. Now we say, wait, there's an acid, this must be a base. I'm expecting water, an ionic compound, and maybe CO2. Well, we made a flashcard one point back that said, oh, wait a minute. That breaks down. That decomposes right away into water. And if you take H2O out of that, what's left over? CO2. So acid, base, salt, ionic compound, water, and CO2. And really the key thing was recognizing, okay, for an acid-base reaction, H plus is going to stick on something negative, put that over there. The leftovers, the cation and anion, are going to give me that ionic compound. And then I had to recognize, oh, that's going to break down. And I also had to recognize that I needed enough acid and enough base to neutralize each other. Let's see if I balance that thing then. I need a 2 there, and I think that's all we need. Now, of this mess, if I was going to do a total ionic equation, I'd say, well, okay, I've got 2H plus 2Cl minus. That's the HCl breaking up. I've got the sodium carbonate, 2 sodium plus CO3, 2 minus. There I've taken the reactants, broken up the strong acid, broken up the soluble ionic compound. Over here, sodium chloride, if I look that up in my solubility rules, I would see that it's soluble. And I would write that. Water is not an ionic compound. It's not a strong acid. There's no reason to break it up. H2O, liquid, and the fizzing. CO2, gas. Big mess, but really it came down to acid base, H plus, sticks to an anion, put the leftover cation and anion together, and we're good. Spectator ions, what are they here? You might stop the video and say, well, wait, what's repeated on both sides? Absolutely identical. All right, you're back. 2 chlorides, 2 chlorides, 2 sodium ions, 2 sodium ions. Those are the spectator ions. So Cl minus, Na plus. And if I were to write that total ionic equation and write only the stuff that actually reacted, 2H plus CO3 2 minus gives me H2O liquid and CO2 gas. Now, I should make that aqueous and aqueous. Molecular equation, I figured out what my products were, balanced the equation. Total ionic, broke up soluble ionic compounds, broke up strong acids. Net ionic, ignore the stuff that was exactly the same on both sides. All right, last page is some practice problems. I think my voice will last another minute or two here. So these are right out of the book, so you can always go look up the answer. But let's see what would make sense here. I had a plan. Now let's do all of them. Okay. What kind of a reaction do we have here? Well, acid base, I don't see H plus. Precipitate, both of these would have to be aqueous, one solid. No, that's not it. It's got to be oxidation reduction. And in fact, there's an element alone. There's an element alone. What's the charge on an element alone? 0, 0. Oxidation reduction. Total ionic equation. Now I'm going to kind of jump right in there. What I recommend is you stop, see if you can write it, and then come back and see what I do. Total ionic, zinc, solid, plus Pb2 plus 2 nitrate on the reactant side. Now again, stop and say, wait, how did that work out? How did he get that? How did I know NO3 stays together like that? Chapter 3, I made a flashcard. On the other side, I've got zinc 2 plus 2 nitrates plus solid lead. Here's my total ionic. I broke up that and that. Soluble ionic compounds. What are the spectator ions? 2 and O3. There and there. Identical. You think of it as algebraically canceling them. What's my net? Survey says zinc solid plus Pb2 plus gives me zinc 2 ions and Pb solid. That's my daughter, if you can hear somebody laughing in the background. I'm not sure what's going on, but... All right. B. I'll leave that one up there for reference. Aqueous liquid. It's not precipitation. But I do notice, oh, wait a minute. That looks like H plus. That looks like, oh, I'll do that one in blue. Dang it. Hydroxide. This certainly looks like an acid-base reaction. There's water. There's an ionic compound. Acid-base neutralization. KOH, one of our rules, I think it's rule number 1, says potassium compounds are always water-soluble, so 2K plus 2OH minus plus. Now, strong acid. Made a flashcard. Now we're fibbing just a teeny bit in Chem 51, but it's reasonable, especially considering the situation we're in. So I'm going to do this. 2H plus SO4 2 minus. Now that's just a tiny bit of a fib, but it's pretty reasonable for Chem 51. Strong acid breaks up, the H plus comes off. On the other side, potassium sulfate, 2K plus SO4 2 minus, plus 2 waters. I have no rules about breaking up molecular compounds. I only break up soluble ionic compounds and strong acids. So I can figure out what can I sort of cancel from each side. 2 potassium ions, 2 potassium ions. Sulfate ion, sulfate ion. Now this is going to look a little funny. 2OH minus aqueous plus 2H plus aqueous gives me 2 waters, liquid. Now there's nothing horribly wrong about that equation, but as you saw when we started looking at chapter 5, balancing equations, usually we want the lowest whole number ratios. So 2 to 2 to 2 to 2, I said, well, that's really 1, 1, 1. It's not really wrong to say 2 to 2 to 2. It's just not conventional. The homework probably wouldn't like it. I don't really care. All right. Problem C. I'm going to leave problem C up to you, but let's figure out what kind of reaction it is. Aqueous, 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 aqueous. It's not precipitation. I don't see H anything. It's not acid-base. By default, it's got to be oxidation reduction. Well, I start looking at these. Fe, that's actually Fe3+. This is tin 2. Over here, iron 2. And over here, tin 4+. If you look at it that way, I'm hoping to say, oh, yeah, I can see. We said elements alone, or if we see that charges have changed, we know I've got oxidation reduction. We've had an exchange of electrons. Okay, I'll let you sort that out. Write the net ionic for that. Again, the answer, 5.14. I don't know if it's 513 or 514, number C. So you can find the answer to that. But, okay. And then 15 kind of, let's do 15 says, hey, any of those that are redox, identify the oxidation and reduction. So I'm going to do this. In A, I've got zinc solid going to zinc 2+, aqueous. And I've got lead 2 ions going to lead solid. And then I remember, what's the charge on an element alone? Just a lead solid, zinc solid. Oh yeah, that's right. That's 0. That's 0. Here, I'll put it in black. 0 and 0. So this charge went up. This charge went down. Now, I think this is the easier one to remember. Whoever had their charge reduced was reduced. So I'd say, oh. What's it? Reduced. Well, the opposite of reduction is charge going up, and we call that oxidation. If I look at C, I've got iron 3+ on the reactant side, iron 2+ on the product side. I've got tin 2 on the reactant side and tin 4 on the product side. And I'm going to leave it to you. You can go look up the answer, but this is a good time to stop and say, oh, wait, what was it here? What would it be there? All right. Sunday night, our sort of semi-regular week will start tomorrow. And the idea is for you to look through this lecture during the week. There's a homework assignment due Thursday, and there is no quiz and no lab or anything else next week. All right, folks, good luck, and I'll be available. I'll be available during the week, and we'll go from there. Okay, bye now.